e colocar para gravar, só para não esquecer.
Eu vou desligar meu celular aqui para não incomodar.
Ok, só mais um pouquinho e a gente já inicia o seminário. Pessoal, vai se logando. Ok. Ana, eu vou fazer uma pequena introdução e aí eu vou passar a palavra para você, tá? Eu acho que a gente já pode começar e as pessoas vão entrando, para a gente não atrasar, né, a nossa agenda. E a gente vai fazer em inglês, isso, né?
Uhum.
Okay. So let's start. Hello, everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today, we have the pleasure of having Ana Lourenço, who holds a master's degree in astronomy and is at the moment a PhD candidate at the University of Valparaíso. Ana's research interests focus mainly on extragalactic astronomy and galaxy clusters and their environments and evolution. Ana also took part in the experiment that confirmed the existence of gravitational waves by observing the electromagnetic counterpart back in 2017. Anna, thank you very much for having accepted to give us a webinar talk today on such an exciting topic. The floor is yours.
Okay, thank you, Rodrigo. First, thank you for the introduction and for giving this opportunity for me to show in my work. For me, it's a great pleasure to present this work to this audience. I can see some friends in the chat. So, because I did my master in Rio and I could meet some of you. So today I will be talking about something that I have been interested in since my master's, which is the impact of galaxy cluster dynamical history in the transformation of galaxies, more specifically on the frequency of the jellyfish galaxies, those famous galaxies that I'll be talking about today. And this work has been done in collaboration with many people, especially collaborators from the GASP collaboration, which is gas stripping phenomena with Muse. The PI is Bianca Poggianti, and some people from my local group here in Valparaiso. The universe in the distribution of matter in the universe at large scale has this filamentary shape, and the galaxy clusters, they continue to grow, creating galaxies from filament feeding and also from spherical collapse. And the galaxies, they permeate the most different kinds of environments through clusters, groups, filaments, and even voids. And in 1980, it was observed by Dressler that environments that were less dense, such as the outskirts of galaxy clusters or voids, they tend to have more spirals, blue star-forming galaxies, while the environments that are denser, they tend to have more elliptical, redder and quenched galaxies. And this is known as the morphology density relation. And this made the astronomers to wonder what kind of physical mechanisms could be responsible for these changes in galaxy populations. So there are several processes that can transform galaxies in those high density environments. And we can basically split them in these two main groups, the gravitational ones that are going to affect all the galactic components, such as the gas, the stars, and the dark matter. But also you have the hydrodynamical processes that can affect only the gas, and some processes that are a mixture between those two processes, the types. So in this work, I will be focusing on one kind of hydrodynamical process, which is the room pressure stripping. And the room pressure stripping is, you can see here in this image of Chung et al. 2009. The hot intracluster medium is being shown in orange, and you can see in blue galaxies that are infalling into this potential well. And while the galaxies are infalling in the potential well, their gas start to be detached from the body, from the disk. So it starts to form these tails. You can see here, kind of, but in this image you can see much better. Here it's showing in H1 and here in H alpha. These are images from Muse, taken from by the collaboration, which I'm part of, GASP. And nowadays we know that that room pressure stripping is one of the most efficient mechanisms at removing gas in galaxy clusters. And also when you have this very large gas stripping here, like we really call tentacles. The galaxies, they start to resemble jellyfish, and that's why we call them like that. So, well, the gas, basically, here you have again an image from the simulation, how the matter is distributed in the universe. And we know, as I show in the beginning of my presentation, that galaxy clusters, they are still growing, and mainly in the intersection of the cosmic web. And cosmological simulations suggest that massive galaxy clusters at the local universe have accreted at least 40% of their galaxies from groups. After these groups, they enter in the cluster, they get disrupted about 1 gigayears after they enter. So observations suggest that 10 to 20% of clusters, also at low redshift, intermediate, are undergoing mergers with other galaxy clusters of similar sizes. So we know basically two ways of this, that cluster growth can impact galaxy evolution in general. So the first one is the group preprocessing, which is basically when these groups, they start to fall in the galaxy cluster potential well. They already, we can see here, like I should explain this by the image. Here are images from Hafet of 2016. And the authors, they identified the subgroups in showing with the black circles, and measuring the gas fraction, the hydrogen, neutral hydrogen, and also the quenched, the red galaxy fraction. You can see, like, organizing those groups by mass beams, that groups already had very high fractions of red galaxies that are H1 deficient. So that means that those galaxies, they were processed prior they enter in the cluster environment. They were processed in those groups. So, sorry. The other way would be by post-processing due to major mergers. So here we have major mergers that are like the most energetic phenomena in the universe since the Big Bang. They can release about 10 to the 64 ergs. And simulations like this one showed from Vijaya Raghavan and Rika, 2013, shows that cluster mergers can really increase the run pressure in those violent environments. And also this other work by Ruggiero, 2018, that is here showing a threshold line of density, pressure, I'm sorry, from the ICM. And every of those triangles and squares are jellyfish galaxies. And basically, these galaxies, they were identified in this work from Roman Oliveira. And the interesting thing about this cluster is that is the system with the highest number of jellyfish galaxies, and it's also a merger of 4 clusters. So we had some evidence from simulations and also observations that you can see here in my references that show that cluster mergers could really enhance the run pressure stripping in those violent environments. So, but in order to draw a strong conclusion about the impact of cluster mergers on the formation of jellyfish, we need to have a large homogeneous sample and classify the dynamical stages and the history of merger of those clusters in a robust way. And to do that, we can use many different proxies from the X-rays, from the radio, from the optical. So let's see how we can search for these relaxed clusters. Here, for example, we can start by the optical proxies. And there are like many different optical proxies to find which dynamical stage that cluster is. The first I'm showing here is to search for several bright galaxies in the center of those clusters. And then you can compute the magnitude gap. So what happens is that in relaxed clusters, you normally have one very big galaxy that's called the BCG, and the second brightest galaxy is not going to be as big as that one. It's going to be very small, so compared to that. So the magnitude gap, when you subtract the magnitude of these bright galaxies with the magnitude of the smaller, the second brightest, you're going to find a very large magnitude gap for relaxed clusters, while for disturbed clusters, you are going to find a smaller magnitude gap. Another way of searching for disturbance in our cluster samples is to apply the Dressler-Sheckman test. It's also a famous test that basically compare the velocity of each galaxy. For that, you need to have redshift, of course. So you can compare the velocity of each galaxy to, for example, the 10 nearest neighbors. And by that, searching for deviations, you are going to have the areas where it's more probable that you have a substructure in that cluster. And this technique was improved by Andrea Biviano. And here I'm basically showing this is a cluster, and each of those gray axes are members, and the field the field circles, colorful circles, are the substructures that this technique of Andrea Biviano is able to isolate, because the normal Dressler-Sheckman test cannot really isolate the members of each substructure. Other methods are to search for velocity multimodality. If it's, for example, distribution is a double Gaussian, you will have a hint that that cluster is interacting. Or projected over densities. Some people use a technique called the DB scan to search for groups in the plane of the sky. And also, you can use Gaussian mixture models to search for multimodality in velocity in the plane of the sky, and also use the plane of the sky and velocity as a third component, and search for multimodality in like 3 dimensions. So the gas that emits in X-rays is collisional. So it's even better to retain information about the past mergers events for longer than the optical wavelength, as I told before. Like the optical substructures, after they enter in the galaxy clusters, they get disrupted after 1 gigayear. So the X-rays can retain that information for longer. So analyzing, for example, temperature and pressure maps, you can have an idea about if that cluster is a pre-merger or a post-merger, if it's relaxed, if it's still is very concentrated and round, probably this is a relaxed cluster. When you have two structures that they start to approach, the gas between those two clumps, it starts to be compressed, and you are going to have a increase in pressure and in the temperature. That's a shock front that's going to propagate through the galaxy cluster, and in the end, these shocks can accelerate the ions in the intercluster medium, and cause this kind of arc shaped that it's about megaparsecs of extensions, and it's known as radio relics. So also in this kind of violent environment, normally the core of the X-ray clump that is cool, it's cold. That's why there is a distinction between cool core, which are like, it's a proxy for relaxed clusters as well, that are normally concentrated in single peaked, and non-cool core clusters that probably they, or they didn't have time to form a cool core yet. They are very dynamically young, or they suffered a recent merger and their cool core was destroyed, was disrupted, and that could generate cold fronts that also propagate through the intercluster medium. And a special kind of cold front that happens when you have a relaxed cluster that suffer just a small merger, like a single massive galaxy or a small substructure that pass through like near the center of a cluster like this, and makes the gas to rotate around the cluster potential well. And you're going to see this kind of spiral-shaped structure that is called sloshing cluster. So, sorry. So here we see again radio emission that can be used as a proxy for cluster dynamical stage, because normally this cluster halo that is observed here, or this cluster radio relic, they are only observed in post-merge clusters. So we can also use this as a proxy for dynamical stage. So before showing my results, I would like to present the sample we use it to perform this work. And our sample is basically wings, omega wings survey sample, and it's a low redshift sample composed of 77 clusters that come from these brightest rosette cluster sample, which is a X-ray catalog, and it covers a wide range of masses, and it can reach very low magnitudes, very faint magnitudes in B and V bands. Also, the good thing about it is that covers a wide range of masses, and it reaches, and also you have a very good coverage, because we have for the wing sample 34 per 34 minutes, which corresponds to this in megaparsecs. And for the omega wings survey, it's like a bigger field of view. So we have field of view from 2 per 2 degrees squares. For these clusters, these 46 clusters that were follow up. So we also have X-ray data that we searched in the archive of Chandra for the wings clusters, and we found 48 clusters observed by Chandra, which is a very good number to make some analysis. So also, another thing about these very homogeneous samples is that it has multi-wavelength coverage, and it contains the largest numbers of room pressure stripping candidates that is known today. Those candidates, they were described in this paper from Poggianti 2016. And then there was this follow-up program by Muse from the GASP survey, described in Poggianti 2017. And here you can see like one of the room pressure stripping candidates observed in SDSS, in H alpha in Muse, and in optical in Muse. And you can see much more detailed tails in this Muse images. Now I'm going to talk about what we did. And as I told you before, there are many ways of classifying the dynamical stages in the different wavelengths. And here, starting from the optical, again, reminding you about the magnitude gap, which is the difference between the magnitude of the brightest, less second brightest galaxy. And other parameters we tried to analyze were the Fmax, which is a parameter we define as the number of members in the richest substructure, let's say this one, for example, divided by the number of members in general. And this would be a good way of identifying, for example, major mergers. Since if you have a high Fmax, you are going to have a big substructure that is entering that cluster. So it could be a way of identifying major mergers. And F sub basically is the number of members in a substructure divided by the numbers of, number of members in substructures in general, in all the substructures, divided by the number of members. So if you have a high F sub, you're going to have a disturbed cluster. So we then have this, in this plot I'm showing here in the lowest part of the, well, first the diagonal is showing the distribution of each of those parameters. And in the lowest part of the diagonal, we have the bivariate scatter plots and the linear fit. And here we have the correlation parameters between the parameters, the correlation, between the two proxies we are using. So we can see that the highest correlation parameter, in this case anti-correlation, is for magnitude gap and F sub. And then we did the same thing for X-rays parameters. We had available from the literature those the concentrations and centroid shifts for our Chandra sample from this paper from U1 2020. And first let me explain what is concentration. The concentration is basically the measure of the flux within two different apertures. So here they use 100 kiloparsecs over the flux within 500 kiloparsecs. And here is the X-ray image of a galaxy cluster. And another method is to compute the centroid in different apertures again. And you're going to have for relaxed clusters that the centroid position will not move a lot when you compare, when you compute it in different apertures. But in disturbed clusters like this one, the centroid can, the centroid position can deviate a lot. So we learned from this that relaxed clusters are concentrated, and also, and the disturbed ones are not. And the relaxed clusters, they have small centroid shifts, and the disturbed clusters, they have high centroid shifts. Another parameter that one can use that is actually a combination between optical and X-rays is to compute the difference between the position of the brightest cluster galaxy, the BCG, and the X-ray peak. In a disturbed cluster, it's not as easy to identify the X-ray peak, but I mean, you can use either peak or centroid, and normally in very disturbed environments, the offset between the BCG and the peak or centroid is going to be high, while in the relaxed systems is going to be low. So here again, we have the distributions, and we have the bivariate scatter plots, and we see that the pair of proxies with the better anti-correlation is concentration and centroid shift. So, so after we had this, we needed to compute the jellyfish fractions. And to do this in a fair way, to compare in a homogeneous way, we need to mind about very different things that can affect this. One thing that we did that was never done before when computing fractions was to consider the same physical radius to make this kind of computation. So we analyzed the photometric coverage of wings and omega wing surveys, and then we had to define centers, because for some clusters it's not as straightforward to say if that BCG is the center or the X-ray peak is the center. Especially for merging clusters, they can have more than one X-ray peak, or they can be very extended in their X-ray emissions, and have many bright galaxies in the center. So we need to find a way to define this, what we are going to use as a center. And then after we did that, we compute the cover, the maximum radius that would cover most completely that cluster. So then we test different coverage, and we found that 0.7 R200 were the radius that maximized our sample for the wings and omega wings data. I mean by that we would be able to have some merging clusters and some relaxed clusters in our sample that fully covered 0.7 R200. Okay, so after that, we can compute the fractions inside that fixed radius with a well-defined center. And we found that, well, we have this way of computing fractions with the number of jellyfish over the number of spirals. And here, because I'm showing the photometric fraction, we need to correct this by the field. Here I'm assuming that the jellyfish galaxies are basically members, because it would be hard to explain why a galaxy is a jellyfish if it's not a member of a cluster. And this field correction was taken from Fasano et al. 2005, 15. So after we computed these photometric fractions, we compared with all the dynamical stage proxies we had. And here I'm showing the main result of this talk, which is that the fractions, the photometric fractions of jellyfish have no correlation, no clear correlation with the environment, the dynamical stage. So you see here very low correlation coefficients. Another thing I would like to point out from this plot is that most of the distributions of our dynamical stage parameters, they are unimodal. So this is showing us that there is not a clear cut between relaxed and disturbed in the most of those parameters. It's more like a continuum scale from the most relaxed to the more disturbed clusters. And by the bad correlation, like the low correlation between the X-ray proxies and the optical proxies, we are seeing actually that those two things are showing two different kinds of things, like the physics involved in the X-rays is different from the physics involved in the optical. So those parameters from the optical that don't correlate very well with the X-rays. So then we tried to understand this better, adding extra information, such as code front, sloshing, relics, and halo. We took those information from the literature. Here I'm basically showing the pairs of parameters that correlate better in the X-ray, and the pair that correlates better, the best in the optical. And I add this arrow to show the direction of disturbance increasing. And we can see that the radio relics and halo clusters, they are over this line defined by Razia 2013, which separates the more relaxed from the more disturbed clusters. As expected, the relics are there because they are like proxies for post-merger systems, which are very messy. And the sloshing, they are mostly lower below this line, which is also expected since sloshing clusters are basically relaxed clusters that suffer small interactions. But looking at the optical, we can see more scatter. Because, as I said, the correlation between the X-rays and optical is not very high. So here I'm color coding with the room pressure stripping fraction, which is the jellyfish fraction measured within 0.7 R200, as I said. And it's more clear here, like qualitatively, we have no correlation between the dynamical stage and those fractions. So then we tried a second thing, that was to visually classify our sample in different dynamical stages, 5 different classes, but including also information from the literature, because some of those clusters, they had simulations. Also, we had information about their substructures, BCGs, positions, everything. So we used everything that we had to classify the sample in those 5 different classes. And the simplest case is the relaxed cluster, which is symmetrical, concentrated, and the BCG coincides with the X-ray peak. The second less disturbed is the mildly interacting class that has small substructures and often is sloshing. The gas is sloshing, like with those spiral pattern I said before. The third class is the premergers. So in premergers, you can have 2 or more substructures of comparable sizes, and they are going to be separated by less than R200. And in projection, they are going to be separated by 3 sigma in velocity, sorry. So the fourth case is the interacting case, which is asymmetrical, is not concentrated, and the BCG very often doesn't match with the X-ray peak. And the most disturbed case is the postmerger. They are very asymmetrical, they are not concentrated. The BCG very often doesn't match with the X-ray peak. And also they can present extended radio emission. Here is a post-merger cluster that has, in white, I'm showing the contours of the radio relics. So then after we classified the clusters into those 5 dynamical stages, we could compare now color coding by dynamical stages with those 2 diagnostics to see how our classification is matching the literature, common used diagnostics. And we see here, for example, that the X-rays, of course, match well because this is more X-ray biased, our classification. And the optical, not that much. And a nice thing we can see, for example, this outlier here is a premerger cluster. So this was interesting to see. And then we use those 5 classes that we classified to try to find some kind of trend, like if the run pressure would increase in some specific classes. So here this plot is basically a violin plot. Every of those black lines is showing a galaxy cluster, and these curves are showing the kernel density estimation of the distribution. So here, for example, for the relaxed, you can see that the jellyfish fractions varies from 0 to close to 0.4, and here from 0 to close to 0.5 in the mildly interacting. And again, we found no trend between the jellyfish fractions and the dynamical stages. So then we can also ask ourselves if the fractions we computed are at the odds with other studies. And I would like to emphasize here that those things are not really comparing the same things, because, as I said, our work was done computing the jellyfish fractions in a fixed physical radius of 0.7 R200, and nobody else did that before. And also here some works, for example, this one from Roberts is showing the fractions of jellyfish in the continuum emission, radio continuum. So it's not exactly the same as the ones that observed in the optical. And also it depends on what are you using to correct, to normalize your fractions, because I used the late type galaxies, And Poggianti, for example, here is talking about star formation rates over then a certain threshold. The same for Robert, that talks about the specific star formation rate. And so while other people just normalize by the total number of members. And one thing we are working on now is to obtain the fractions of blue late type as well. But we already have that for the spectroscopic sample that I'm not showing this work, just for simplicity. And we are now obtaining for the photometric sample, and we know that the results, they don't change even after those extra corrections. We already saw that. And so another thing we analyzed was the jellyfish fraction, how the jellyfish fractions varies with mass, cluster mass. And this was a very unexpected result, because we know, well, from room pressure depends basically on the density of the intercluster medium, and depends on the square of the velocity of the difference of the velocity of the galaxy to the intercluster medium. So then those two things, those two parameters are expected to be higher in massive clusters. So, and here we are seeing that the massive clusters, they don't hold the highest fractions of jellyfish. So some take-home messages are that we found no correlation between jellyfish fractions and the dynamical state proxies we used. Another is that after classifying the sample into those 5 different dynamical state classes, we also found no hints of possible enhancement in jellyfish fractions in those specific dynamical states. And we also found no apparent correlation between the room pressure stripping fractions and the cluster masses, or the jellyfish fractions. It's basically the same. So the next step, just to finish, is to extend the radius of this analysis to larger radius. For that, we're going to need the spectroscopy in more like in larger radius, and also photometry. Then omega wings can provide us. And here are my main collaborators, and I could take the questions now. Thanks.
Thank you very much, Anna, for this very interesting talk. Now we have some time for questions. If you joined us on YouTube, please put your questions in the comment section. And if you joined us here on Zoom, please raise your hand and ask yourself. So questions? Okay, Rogério has a question. Go ahead.
Hi, can you hear me, Anna?
Yes, very well.
So first of all, thanks for the nice talk. I have 2 questions. Maybe I misunderstood, so I first want to confirm with you. My first question is about the definition of Fmax in the slide number 15.
Okay. Okay.
Great.
Okay.
So it's the ratio, the number of members in the initial substructure over the total number of members. Okay.
Yes.
So I mean, for disturbed clusters, what value of Fmax do you expect?
So this will not really segregate into, well, it doesn't really segregate into, it's not a good parameter to segregate between relaxed and disturbed, but is a good parameter to segregate into like the major merger class, because if you think the major mergers, they are going to be collisions between like a cluster and a large cluster as well. So if you have a substructure that is very large, this is going to be like a proxy for a major merger. So for example, from this plot, we can see like this little peak. Maybe it's just one galaxy cluster. Maybe there is another one here. That would be two major merger clusters, probably.
Okay, great. So, okay, another comment, it's regarding our take-home message. When you see the plot, the mass of the cluster across the jellyfish ratio. Yes, this mass refers to the more massive cluster, the sum of the masses.
These masses are showing like the mass of each galaxy cluster that were computed with velocity dispersion.
Okay. Did you, just for curiosity, check it? Any dependence, considering a binary merger, the mass ratio? I mean, a major merger, a minor merger. If you see any difference among the jellyfish fraction among these classes?
Not really. This is something we can do. Yes, like to compare. I do have information about mass ratios from clusters that were already simulated. So, but it's the problem is that we don't have like a large number of clusters with simulations, you know. So it's going to be hard to have robust statistics from that.
Yes, because I'm curious to know if, for example, major mergers would induce a larger fraction of jellyfishes than minor mergers, for example.
What is shown here? Actually, we showed that not here, because in this part, like the ones we have. Like the radio relics, they are major mergers, I remember. And they are like not with very high fractions of jellyfish, right? You see the yellow dots, like the highest fractions are more like to this relaxed part.
Okay, I see. So thank you very much, Anna. And again, thank you for the nice talk.
Thank you. Thank you for the question, Roger.
Thanks, Rogério. We have now a question. We have a question from YouTube. Rubens Machado says, thanks, Anna. Could you comment on the spatial distribution of jellyfishes within a given cluster?
Yes, thanks for the question, Rubens. So this is one of the next steps of my doctorate, is to analyze the distributions of jellyfish in and around those substructures. For a while, from what we know from general analysis, we kind of see that jellyfish, they are avoiding substructures. But we need to analyze this more detailed case by case with this kind of image, for example, and try to draw some statistics about it. Yeah, but it's a very interesting question.
Okay. Thanks, Anna. Lourenço also is thanking. It was a wonderful talk. More questions? I have a question. How do you identify those sample candidates that you are studying? And also this and another second question is you talked about the fractions of jellyfishes within clusters, but how common are jellyfish galaxies?
Yeah, so the first question, well, I don't have a slide really showing that, but in this paper from Poggianti 2016, 3 different classifiers analyzed the images of the galaxy clusters, the galaxies, and they had no previous information about their environments. So they gave, they rate those galaxies with, if they were jellyfish, and if they could be jellyfish, they were rated between from 1 to 5. The 5 case would be the ones that are the most amazing, with most amazing tails. And so yes, it was basically from the optical image from wings and omega wings. And then after, if there was disagreement, they had to sit and come to an agreement about those galaxies. And the second question, what was the second question?
The question was how common are jellyfish galaxies?
Yeah, so this is basically what we are trying to answer, like when we measure these fractions, right? We are trying to understand, for example, in Vulcani et al., they use blue lake type galaxies as a proxy to the first infalling populations. The galaxies that are first infalling, they will be more blue and spirals, as I said in my introduction. And from that, you have an idea, they found just using spectroscopy that 35% of the galaxies were jellyfishes. Now, I would like to make a point that this term jellyfish actually in some works, it's used just for the galaxy with the amazing features of tentacles, while for the others that are not that amazing, that are shown, are called as run pressure stripping candidates, or run pressure stripping galaxies ongoing run pressure stripping. And yeah, so I'm talking about jellyfish to make things easier to understand.
Sure.
But maybe jellyfishes that is like these galaxies with the very large tentacles could be a very special case of run pressure stripping galaxy. Yeah. They could be like that because of special conditions. So.
Sure. Well, thanks. We have time for a last question. Let's wait a little because we have a delay with the transmission in YouTube. Okay, well, if there are no more questions, I think we can wrap this up. First, I'd like to thank everyone for attending this webinar. It was a very nice webinar, and a special thanks to Ana Lourenço, who make herself available to give us this amazing talk. Thank you, Ana, very much.
Yeah, thank you again for the opportunity.
Okay, so thank you everyone for attending. Everyone have a great day, a great week, and I hope to see you all again back on our next webinar. So, goodbye.
Bye.